Welcome back. In this video, I will introduce the types of biochemical reactors and their mass balances that leads to their design equations. In general, chemical processes can be classified as batch, continuous, or semi-batch processes. For a batch process, there will be no mass crossing the system boundary. For example, if we consider a pot on the stove, we only add stuff into the pot before the cooking process begins. And if we draw a system boundary within the pot, there will be no in and out during the cooking process. Similarly, in chemical processes, if we have a vessel that is enclosed and there is no in and out, and it only has the things that it has in the beginning, it is a batch process because no mass crosses the system boundary of that vessel. Chemical processes can also be continuous process, where the inputs and outputs flows continuously through the system boundary. For example, if we have a pipe, then if we consider the system boundary as part of the pipe, see that the fluids will flow in and fluids will flow out. There is an in and out across the system boundary. Beside the example of a pipe, we can also consider some of the most common operations in chemical engineering, such as distillation columns. Distillation column is a continuous process because there is feed and there is output. There is something going into the distillation column, and there's also something going out of the distillation column. Therefore, it is a continuous process. Chemical processes that are neither batch nor continuous are called semi-batch processes. These kind of processes can have either only an input without output, or it can have no input, but it has an output. So it can either have in or out. If there is no in or out, it is a batch process. If it has both in and out, it is a continuous process. If it only has in or only has out, it is a semi-batch. To make things more specific and consider biochemical reactors, they can also be classified as batch, continuous, or semi-batch reactor. For example, batch reactor has feed put into the reactor before the reaction starts, and it has no inlet or outlet during the operation. Therefore, batch reactor is a batch process, and we usually draw it with a vessel with an agitator that mixes the content within the batch reactor, and it usually has a constant volume V. For continuous process, we have continuous stirred tank reactor, or CSTR, and in biochemical reactors we call it chemostats. They have inlets and outlets flowing continuously in and out of itself. We usually draw CSTRs with a vessel with a volume V with an agitator, because it is continuously stirred so that the content is homogeneous or having the same composition. It has an inlet and an outlet. Therefore, it is a continuous. And for semi-batch reactor, either it has feed added to the reactor or the reactor content is drained during the process. We draw it with a vessel that has either an input with an agitator or it has an outlet. This mimics when this is the feed batch reactor. That mimics we adding feed during the process but not taking anything out. And the other reactor has its reactor content drained so that equilibrium can be made. To design each reactor, we will need to understand their mass balance and derive its design equation. And the foundation of mass balance is the conservation of mass. The law of conservation of mass says that no mass is created nor destroyed in a physical or chemical process, and in this case we're specifically not talking about nuclear reactions, and we're only considering simple physical and chemical processes. Because no mass is created or destroyed, the mass balance of each chemical species can be considered as something that's going in for a control volume For example, we are interested in some volume, and there will be some inlet going into the volume and some outlet going out of the volume. And the volume itself can have chemical reactions that generates some chemical species by chemical reactions. And there can be accumulations within the controlled volume. Note that the accumulation is not specifically anything going in or out where it's generated. It is the sum of inlet minus the outlet plus the generation, and that equals to what's accumulated within the controlled volume. And this mass balance is the foundation for chemical engineering, where in minus out plus generation equals to accumulation for mass. We can write each term out using mathematical symbols, where the first symbol in represents the mass flow rate of species I going in, and the out can be denoted as the mass flow rate m dot of species I. Then the generation is g of I, species I. Tilde represents is on a mass basis, and the accumulation is the change of mass of species I with respect to time. So we take the derivative of the mass of I with respect to t. This mass balance holds true for every chemical species, and if we divide the equation by the molar mass of the species, molecular weight of species I, we can convert the mass basis into a mole basis. So we convert the mass flow rate into molar flow rate, represented by n dot. This general mass balance will be the basis for deriving the design equation for biochemical reactors. The method of deriving specific equations from a general equation in chemical engineering is called the top-down method. Usually, we would know the inlet and outlet molar flow rate, and the accumulation can be calculated from the inlet-outlet as well as the generation term. The generation term can be related to the reaction rate per unit volume, R of I. And because we're not assuming the reaction rate is uniform across the volume, we need to integrate it across the whole volume to get the generation and destruction across all the volume. However, if we make the assumption that the reactor is spatially uniform, then we can get that reaction rate is independent of volume, that we can take it out, and the volume is V. The generation term would be the reaction rate multiplied by the volume. Let the content of reactor be spatially uniform. Usually we need it to be well mixed. This can be achieved by adding agitators to the reactor. Now let's use the top-down method and derive the design equation for batch reactor from general mass balance. For a batch reactor, we assume that there is no inlet or outlet, so the molar flow rate in and the molar flow rate out is equal to 0, and therefore we have the generation term is equal to the accumulation. So what is produced is what's accumulated. And for a non-spatially uniform batch reactor, we can say that the accumulation is equal to the generation term, which is the integral across all volume of the reaction rate of species I. If we assume that the reactor is spatially uniform, and to achieve spatially uniform reactor, we should assume that it is well mixed. Then we can take out the rate term because it is independent of the volume. So the term will become the rate multiplied by volume. And this equation is the design equation for a well-mixed batch reactor. If we have a constant volume reaction, then we can rearrange the equation so that the we can solve for the rate of reaction. The rate of generation or reaction be equal to 1 over the volume multiplied by the accumulation. Because the volume is a constant with respect to T, and we notice that the moles divided by the volume is just equal to the concentration of the species. So we can rewrite this equation as the rate is equal to derivative of concentration with respect. We can describe the rate in the batch reaction, this equation. If we apply the general mass balance on the CSTR or chemostat, we can assume that it is operated at steady state, meaning that there is no accumulation. There's no accumulation, the accumulation term will go to 0. Anything that is with respect to T is going to. And if we write out the generation term will be the integral of the rate of reaction with respect to the volume over all the volume to 0. And if we assume we have constant volume, and if we also assume that it is spatially uniform, that is, the reactor is well mixed because it is constantly stirred, then we can take out the term so that it becomes rate of reaction multiplied by the volume. Now if we rearrange the equation and solve for the rate R of I, you can see that it is Ni minus Ni naught divided by volume. This equation is the design equation for CSTR or chemostat. For semi-batch reactor, let's look at a special case of a feed batch reactor where there is no outlet but only inlet that we feed in. The outlet, N of I, go to 0. We also assume that it is well mixed and therefore spatially uniform, so that the generation term will be the rate of reaction times the volume. However, this time, because we're feeding things into the reactor, the volume of the content is dependent on T. Therefore, if we write things out, we have the inlet plus rate of reaction times volume with respect to time, which is the generation term, is equal to the accumulation term. Solve for the rate of reaction, R of I, we get that it is equal to the accumulation minus the inlet divided by the volume with respect to time. This equation is the design equation for a feed batch reactor. In this video, I went over the types of chemical processes and types of biochemical reactors. And we derived the general mass balance using the conservation of mass. We apply the general mass balance to each of the biochemical reactor and derive their design equations.